So can you all hear me? Good. So Tom Claytor and I, from the very beginning of this cold fusion scenario, have been involved with many different experiments. And it was clear right from the beginning that it would be nice to be able to measure small amounts of helium in deuterium and other gases. And there was much discussion about doing that, but not too much was done until about 18 months ago or so. And I started getting involved with this, and we kind of sat around and discussed what you'd need to do this. And so we started putting together a system. And for those of you who were at the ASTI meeting in Italy about a year ago, I talked a little bit about what we had done up to that time. And what I want to do today is just sort of start over with that and tell you what new things that we've done so far. So the question is, what's the problem and why is it difficult? The problem is that we need to be able to separate and quantify extremely small amounts of helium in essentially pure deuterium or some other gas that one is working with. Why is it difficult? It's difficult because most typical mass spectrometers don't have the kind of resolution that you'd like to have to be able to do this. The difference between helium and deuterium is only 25 millimass units, and so that's pushing pretty hard for something like an RGA to do, but magnetic sector machines can do that. The more important issue is that most instruments don't have the dynamic range you want. I mean, if you're starting with pure deuterium and you're looking for parts per billion of helium in the deuterium, you need a dynamic range of about 8 or 9 orders of magnitude, and most instruments can't do that. So you're left with a situation about you need to separate the helium from the deuterium or whatever else you're going to use. The other problem, which is really serious and it's not very often addressed, and that is that ambient air is about 5.2 parts per million helium, and so we're living in the bottom of an ocean of helium, and so the experiments, in order to be believable, have to be very carefully made. I mean, and high vacuum technology and so on. So, so let's look at the problem a little bit differently. This is a table of the masses of some of the light ions that we're interested in. The two in yellow are helium and deuterium, and there you can see the masses are highlighted there. And again, as I pointed out earlier, they only differ by 25 millimass units. So that's pretty hard, but if you can get rid of the deuterium, that's a direct measurement. On the other hand, if you look at the green guys, if you wanted to measure, say, helium-3, you've got a bunch of contenders to the throne, which are much closer in mass than the helium and the deuterium were. In addition to that, the major background in most high vacuum systems are water and hydrogen. If you've got hydrogen at any significant amount in there, then it gets ionized in the ion source for whatever spectrometer you're using and provides a source of ions that then can react with other things like other hydrogen or deuterium. So you can make HD, for instance, in the ion source, and that's a problem you can't fix by doing chemical separations. That's generic to the device you're using. And this is sort of illustrated in this picture. This is a case where I got aware of this when I looked at the ratio of deuterium to hydrogen in just normal hydrogen. And it's about 10 to the minus 4. So I thought, well, gee, I can put some pure hydrogen in my system and I should be able to see the DH at mass 3. And so we did this and got this plot, which is shown here. And that is kind of interesting because as you increase the pressure of the mass 2 hydrogen, the mass 3 peak increases like the square of the pressure. So it's not, I mean, the bottom line is it's a bimolecular reaction where the products are being, or the reactants and the products are being made in the ion source. And so there's not, without changing the geometry and so on, there's not much you can do about this. And so this kind of limits, this kind of a reaction product limits the dynamic range that you can try to measure mass 3 in if you have significant amount of mass 2 in the system. So that's another issue that we've been chasing. Even more probable reaction, of course, is the reaction between hydrogen, which is in the system, and H+, which is made in the ion source from the hydrogen to make H3, the triple plus, and that's also at mass 3. And so that's actually probably what's actually being shown in this picture. So that's an issue that one has to worry about. So anyway, we looked at the concept of how we would do this, and we had thought about early on trying to chemically separate the deuterium by, say, running the sample over hot copper oxide and reducing the hydrogen isotopes to water, which we could trap out and then look at what was left. I didn't like that much because you end up using up the materials and you have to continually replace them. The other possibility would be to use some kind of a getter material, which has the same problems. And the getter materials, from my experience in trying to purify helium-3 from tritium, is that it's kind of a slow process, and you have to circulate the gas for a long time to do that. So we kind of got away from doing these chemical reaction things and decided maybe we could use cryogenic chromatography for that. And so we had this kind of a picture that you see here in the back of our mind, and we started trying to put the parts of that together. And so we did that. One of the questions we had was for the size of the columns that we had available and we're going to use, did we have sufficient capacity in the columns to take care of the samples we were going to run? And so here's an example here where we ran pure nitrogen into the system at sort of 1 atmosphere pressure and 50 cc's, which is about 50 times the size of the samples we were anticipating running. And so you can see here that in the first 10 minutes, you've got more than 90% of the gas is absorbed, and then in 20 or 30 minutes, it's pretty much all gone. So that looked pretty promising. The situation for air is not so good. It's slower and it takes longer, and I don't understand the reasons for that quite yet. I think that maybe some problems with we're loading the very front end of the column and decreasing the conductivity into the column. But nonetheless, it still is more than adequate for the experiments that we wanted to run. So we put together that conceptual system that I showed earlier, and this is a plot of one of the first experiments we did, which was running a mixture of hydrogen, helium, and nitrogen through the system. And the horizontal lines that you see there, the top one is water vapor. It's slowly decreasing as the system cleans up. The blue nitrogen line is essentially constant. The line for hydrogen is essentially constant. With the line for helium, you see this pulse come out. So this looked really good to us. The bad news about it is it's not a very efficient system. The RGA is not very sensitive on a relative basis, and the baseline is pretty noisy. So we made several modifications to the system. We added a magnetic sector helium leak detector, which was going to be our helium detector. It turns out it has much more stable background and much more sensitivity than the RGA did. And we added some digital oscilloscopes that would allow us to digitally record the data, and we can process it afterwards. Put in a bunch of pressure gauges, and we kept the RGA because we wanted to make sure that whatever gases were coming through were what we thought they were. Nothing was leaking through the system. And so that system ends up looking like this. It's similar to the conceptual system, but got more knobs and bells and whistles. And we originally had thought about having 2 traps in the system. We're going to use molecular sieve and charcoal. And we did that, and this system performs pretty well. This is an elution curve for helium using about 26,000 torr cc's of gas, which is about 1/3 of the sample size of the previous plot I showed you. So things are getting better, but there's still quite a bit of tailing in the elution curve, and it takes a long time to get the gas out. So we went back to the drawing board and played a little bit more, see what else we could do to it. And we added a few more features. Up in the upper left-hand corner, you can see the sample reservoir. That's this 50 cc cylinder that we put the samples into, where we can accurately measure the pressure and the temperature, so we know how many moles of gas we're putting through the column. We got rid of the molecular sieve column. We added over on the right side, halfway down, we added a MKS microvision RGA, which allows us to look at masses 0 to 6. And then we also added in near the bottom there a Keysight 6.5 digit logging voltmeter. This is a really slick instrument, and it puts out, it'll sample at whatever rate you want it to, and then it'll transfer the data out directly into an Excel file that you can then play around with later on. So that was a big step up for us. And that Keysight meter was one hell of a lot cheaper than the Tektronix DPO 7254 we were using before. So here's the deuterium response of the MKS microvision RGA. It's pretty clean. Has a full width at half maximum of about 0.02 AMU, which is, if all other things were being equal, is in pretty good situation to be able to separate the deuterium and the helium. So this is the deuterium peak here, and on the next one is a mixture of deuterium and helium. And you can see the helium is at slightly lighter mass than the deuterium is, and that would still be okay, except you can see there's not a huge dynamic range here available. In other words, if the helium was a couple orders of magnitude, or sorry, if the deuterium was a couple orders of magnitude bigger than it is in this plot, then it would be spilling into the helium, and so it makes it difficult to do this. Here's another case where it's actually the same data, but on a different vertical scale. And you can see on the low energy side of the helium peak there's a lot of tailing out. So that tailing, if it's also coming from the heavier mass peak, will spill into the guy you're wanting to measure. And so I thought it was going to be pretty difficult to do quantitative measurements here. On the other hand, we can use this for a quality assurance thing. I mean, if we think we've gotten rid of all the deuterium, we can make this plot, and if we don't see anything, we're in pretty good shape. So here's the sort of the latest version of our response curve. This is 1,250 torr cc's, which is 50 cc's at 25 torr. It's about half the size of the sample we normally would run. We normally have sort of standardized on 50 cc's of gas at 50 torr. You can see the signal here. I've just put it out in volts. The magnetic sector machine can put out up to 100 volts. And so this 50 cc's at 25 torr of 12 part per million helium is running the thing up close to full scale. And so that's sort of the upper limit that we can handle with the machine. Now we can always make it smaller by using lower pressure in the 50 cc gas. But looks pretty good. It's also eluting out, in about 100 seconds, we get most of the gases eluted out. So that makes the peak amplitude larger. So it looks really, really pretty good. So how do we calibrate the system? That's another issue. And what we've done until now is item number 2 there, where we've prepared standards that we know the composition of, and we then analyze that using the same conditions that we analyze an unknown sample, and the ratio of those two then until it gives us the concentration. On the lower right side there is a calibration curve for the 12.8 part per million standard that we use, and it looks pretty good. The other standardization method listed number 1 there is more interesting if we were trying to desorb some foil or something and we don't know when or where the gas is going to show up. We can continuously sample the system and then integrate over wherever there's some interesting time. And that we can calibrate using a standard leak, and that's incorporated into the system automatically, so we can do that now. We have a lot more experience with the operating with samples done in the second point there as in the first, but I'll talk some more about why we would like to do that first thing in a minute here. So here's some more standard data that I've collected over a while. And if you throw out that one outlier at 6,000, the rest of the other 5 or 6 or 7 samples there have about a 3%, 4% standard deviation in their guys. And so it's not as good as I'd like it, but it's also not so bad. And here's another calibration check that I've done where we've compared the MKS RGA data with the magnetic sector machine, and one would hope that that was a straight line. It's got some curvature to it, although I'd point out that all of the samples that are down there in the lower left-hand corner are all right at the detection limit, and these have not been corrected for background in the machine, so those points would all drop by quite a bit if we did that correction, so that would straighten that out a little bit. But even like it is, I think it's fine for the kind of measurements we want to make. Okay. So we've done a bunch of gas discharge experiments with Tom Claytor, and we've looked at a number of those samples, and here's some of the results are sort of summarized here. But the bottom line is, down at the bottom there, we've made these measurements that give us sort of 20 to 70 parts per billion helium with some fairly large uncertainty. But that corresponds to maybe 20 to 80 milliwatts of power being generated spread over 24 hours, and while the discharge was running at a few watts, and so it's pretty iffy whether you can really believe those guys or not. So let me summarize. I think I'm good here. We've put together a system that we can measure small amounts of helium in gas samples, and currently we could, as an example, can measure the amount of helium in air with an uncertainty of about 10% using a 50 cc sample at 50 torr pressure. These measurements take about an hour to complete, but then to regenerate the traps and stuff takes several hours to get ready for the next sample. And to date, at least as of last week, we had run about 185 of these analyses, with most of them being samples of standards in blanks. Interestingly enough, we detect small amounts of helium in almost every gas sample we've run. And some of them have larger amounts of helium than others, but almost always, if there's large amounts of helium, there's large amounts of air. So I think we're really just looking at the amount of air contamination most of these samples have. as I pointed out earlier, most recent standard runs have a scatter of about 5% at the 1 standard deviation level. The baseline measurement in the instrument at mass 4 is about equivalent to 10 to the minus 10th atmospheric cc's per second leak rate with an uncertainty of about 30%. If you integrate that over, say, the 100 or 200 seconds that it takes to make the measurement, that corresponds to something like 10 to the minus 8th atmospheric cc's of gas, or about 3 parts per billion in our standard sample. So this sort of sets the lower limit that we can go to in terms of our sensitivity. Future work. We fabricated a tube furnace that we were hoping we could put foils in and heat them up and desorb any helium that's in them. What we found out is above about 300 degrees centigrade, the quartz becomes sufficiently permeable that we see significant amounts of helium coming in from atmospheric helium outside of the container. So we got rid of the quartz and tried 304 stainless, and we found out it was just about as bad as the quartz. But I think 316 stainless or 321 stainless may be better. We haven't tried that as yet. We're also looking into some methods to protect the heated tube from atmospheric air, either with another coaxial tube around it that we put inert with something or we evacuate. So, and so those are steps in the right direction. I think I've about covered all I'm going to cover. I'd like to make sure that we acknowledge support and encouragement from Industrial Heat. They've provided quite a bit of service or support for us, and that's ongoing. So that's yeah. Any questions?
We have time for one question. Better hurry, Mike.
Hey, Malcolm, I feel your pain. Nice to get some sort of internal blank. You know, helium-3 would be lovely if you could make the ratio measurement, but argon is kind of nice too. Yeah. If you want to know whether the sample came from air or not. Are you gonna incorporate argon measurements and do some ratioing? Or?
Well, one of the things that we've done recently is in that system between runs, we have to purge the columns, and we do that by flowing argon backwards out through the columns to keep anything that comes off the columns from getting into the magnetic sector part of the machine. And so I got interested in how good that argon is, and so we actually analyzed the argon 3 times, and the average result of that is that argon is about 2 parts per billion with an uncertainty of about 1. And so I think we can measure things at low level. Doing helium-3, I think, is a real problem, but for all the other reasons I talked about, these other molecular species that get made in the ion source, and there's not much you can do about that. So adding helium-3 is an expensive way to not get an answer, I think.
Yeah, well, we can confirm that, actually.
Thank you.